In this video, we'll discuss about the CO2 capture on the potassium carbonate in the presence of water vapor. So potassium carbonate I've taken as small crystals that are filled. Maybe you can see this is the domain what I have selected, and until this point I'm trying to fill with the potassium carbonate crystals. So all these are potassium carbonate crystals that are what you are seeing on the right hand part of the screen. So when the air, I mean the nitrogen and carbon dioxide and water vapor, so these three species combinedly will try to flow over potassium carbonate. So when that happens, potassium carbonate would react with CO2 and H2O, and it gives potassium bicarbonate plus heat. So now we need to try to model this in Ansys Fluent. Trying to model in Ansys Fluent. And the boundary conditions what we had select is H2O, CO2 both as 0.1 mass fraction, and the velocity of the combined species, the air, would be around 0.05 meters per second. And these particles, what you are seeing, these are the carbon K2CO3 particles, which is are of 0.0001 meter diameter. And I'll try to patch this region entirely with these particles. So each cell I'm trying to patch with one particle, and I just want to make these particles stagnate. So even though airflow is there, the particles won't move because the air velocity is bit low. So then I'm trying to assume these particles will stay at its location. So for in order to make them stay at its own location, I'll try to incorporate an UDF saying that it should not move. So how it will not move is with respect to the drag. So if the particle takes the drag, then particle will try to move along with the air. Right? As you know, when there is a particle and air flows across this, so due to this drag force, the particle moves. But now I'm making this drag force as 0 with the help of an UDF, so that the particles which I am trying to patch would remain at its own position. It will not move, right? And now I'll be using this Arrhenius rate for the reaction. So this is the AR is the pre-exponential factor, and BTR is the temperature exponent, ER is the activation and energy. So with respect to these three parameters, we can calculate K, which is called the rate constant, and that rate constant will be multiplied with the molar concentration of CO2 and H2O. Finally, this gives the net rate of the reaction. So with this rate of the reaction, the K2CO3 will be converted into KHCO3. So all these 8 AR, beta R, ER would be mentioned. Beta R for this time being I've taken it as 0, and AR and ER would be given in the Ansys Fluent window. I'll show you how can we incorporate those things. And from that reaction constant, rate constant will be calculated. So this is nothing but this rate constant, and these molar values, it is 1 or 2 you can explicitly mention in Fluent, and with respect of these total reaction will be calculated, and with respect to that reaction rate we can see K2CO3 converting into 2KHCO3 plus some heat addition. So for that heat addition we need to explicitly mention the standard state enthalpy of K2CO3, CO2, H2O and KHCO3. So when we mention the standard state enthalpy of formation, from these values automatically it will calculate the net amount of heat added. So because 2 into standard state enthalpy of KHCO3 minus K2CO3 standard state enthalpy minus CO2 standard state enthalpy minus H2O standard state enthalpy. So this will finally gives the net amount of standard state enthalpy present, and when try to multiply with the kgs we will get the heat that would be added into the system. So I'll now get you through the Fluent how we need to approach this. So for demonstration purpose, I've taken this simple mesh So I have created only two bodies. So one is this lower body, other is upper body, and you can see. So simple mesh I have selected and taken. Just a normal mesh without any size settings. I have given a 5 power minus 3 as my body sizing, and I've created. And this is a flue gas inlet, and this is nothing but it's just a wall and outlet. This is outlet, and these are dem body where I need to patch, and this is the remaining fluid body which I'm not patching with the particles of K2CO3. H2O inlet is nothing at H2O inlet. I have taken both on this side only. So this is also a wall. We can consider make it as a wall in Fluent also. I'll just show you. I'll open the setup. This is a setup. So I'll go to general, which is a steady state I'm taking. So it is a steady state for flow, but transient for the particles absorption. Okay. Now in the CO2, also I'm activating the gravity, and here I've created the minus 9.81 as my direction, and also, and I'll now let you show now how to model this multi-species. So I've taken the carbon dioxide, nitrogen, oxygen, potassium bicarbonate. So all these properties I've taken from the internet. Okay, and the potassium carbonate. Or maybe I can activate the species model because we need to create a multi-species, and we need to have a particle surface reaction where K2CO3 is a particle and it reacts with CO2 and H2O. So I'm activating the particle surface reaction also. So we'll take a finite rate, stiff chemistry solver, and we'll click OK. After that, this is been created. Go to mixture template. In the names, I would add carbon dioxide also, nitrogen as my last species, and I don't want oxygen now, right now. I'm removing that, and potassium carbonate and potassium bicarbonate in the species list. Now click OK. So these are the solid species which will be present on the particle. So initially it is potassium carbonate, but later on it will turn into potassium bicarbonate. So I'll be using the mixing mass weighted mixing laws for all these things, and then I'll go to my injections. I'll turn on discrete phase with unsteady particle tracking for one number of time step, and I'm not using anything right now. I'll increase the number of steps so that nothing will be going to infinite loop. It will be updated for the loop. Then I'll go to the mixture template, and in the finite rate reactions, so I'll be giving the particle surface reaction. The particle surface reaction, potassium carbonate. So there will be three reactants reacting with CO2 and H2O to form potassium bicarbonate. I'll take the pre-exponential factor as 55, right? And as I stated, the rate exponents are 1. If it is 2, then these would be having a power of 2. As it is a 1, so we are leaving it as a default values. And potassium bicarbonate stoichiometric quotient is 2. Then I'll click on OK, change create. You can just also verify the standard state enthalpies here. Potassium bicarbonate and carbonate, what I have selected, these are the values what I got from internet and I've substituted. And you can also substitute so that according to that heat would be added onto the things. Then I'll create a new injection. So now it is a combusting, and I'll select the file case of thing, and I'll select the stop time at 0.001 second. So within one time step, I just want the particles to be injected, and those should not be re-injected again and again. Only I want one time injection, so I'm giving the stop time as this value, and I just need to mention the file also. So this is the file what I'll be getting onto the things, and devolatilizing species should be the species which is not participating in the reaction. There is no devolatilizing species, but we are just mentioning, and we need to activate the custom surface reaction where there is a surface combustion. That is what important here, and inert heating, and remaining you can make it as inactive. Click OK, and we haven't selected the particles. The potassium carbonate is the particle what I have selected for this injection. So you can see the potassium carbonate. Now you can just go to potassium carbonate combustion particle, scroll down, make this as a multiple surface reactions. There will be two surface reactions what I need to have. One is a potassium carbonate to potassium bicarbonate, or potassium bicarbonate to potassium carbonate. Both can happen depending on the reaction rates and the heat what we supply. And I'm saying that there is no volatile component fraction, that's so that would be zero. Everything is combustible, so everything is present in the potassium carbonate. It will react with CO2 or H2O to form KHCO3. After that, again you go to injection. In the multiple reactions tab, you need to mention, so individually or instant, at that instant of the initial moment, the entire particle or the substance is completely with potassium carbonate. There is no potassium bicarbonate. What does it mean? Oh, sorry, this is what it means. Then we'll be giving an inlet velocity of 0.05, so I've mentioned it 0.05, and this with the species of 0.1 and 0.1 at the inlet, and the temperature is 335. So I am taking the reflect as my boundary condition before, because if you don't take reflect as boundary conditions, then the particles will initially inject and it can may go out of the things. But with, if you want it should not go out of the things, I'll just show you what is the UDF I have integrated. This is a UDF I have integrated, saying that drag force is zero, and I'm trying to return the drag force with respect to this macro DPM drag. So the drag force is zero, the particle cannot travel anywhere, and I'll hook this drag force. So I have just integrated this. You all know that functions compiled, and you can just add the drag force. Maybe I'll just once again, for your information, I'll just remove this and I'll freshly add that. This is a previous one what I have executed and compiled. Now I'll just recompile and build and hook that. Load it. That's it. You will see the particle drag force. This is the macro name that you're able to see, and where you have given this. Now just go to injections tab. You can drag drop and you can see particle drag force. As the particle drag force is zero, it will not move with respect to the velocity what it is. Click OK. Then I'll just want to show you the file also, how exactly it's look like. This is a file where it has all the cell coordinates of the DEM body. I mean the body what I have shown it to you. This is the DEM body what I've shown, and for this body there will be a mesh, and each mesh, so the mesh will have individual cells. These are the cell coordinates, and at that cell coordinates I'm saying that there is no velocity to the particle, and this is the dia through which it need to pop, I mean which it need to have. So the dia is 0.0005, not 0.0001, it's a 0.0005 meter, and the temperature of the particle is 300, and this is the mass flow rate of the particle. So with respect to this, the number of particles will be injected at the first time step itself, because I am asking it to inject only for particle time step as 0.001. The stop time is also 0.001. It will only execute one time step, so one set of particles will be initialized. Maybe then I'll just select initialization, and I'll select initialize. I'll just run for one particular transient time step of the particles, the DPM. So that is 5. So we should run 5. I'll make run for 5. I'll let calculate, and I'll just show you how the particles. So the warning you can neglect, because there are no gas phase reactions. We have given only particle reactions. That is the reason it is showing warning. It's not an issue. Now I'll just show you the particles how they are injected. So these are the particles that are injected. I'll just zoom in for you. These are the particles. Maybe you can increase a tracking style with Scaling 3 apply. So you can see it's more spherical in nature, right? And maybe I'll keep an auto range for this, mentioning it as a 5. So I've already kept that. I'll just show you. Yeah, this is the range minimum and maximum what I've selected for this. And then also I'll highlight a vectors. From these I'm computing a vector also. It's just started. It's not yet converged. So these are all the vectors. You can see there is a drop in velocity and there is a reversal flow rate also, because the particles are obstructing the flow. So that is all obvious from this particular vector diagram. You can see vectors are pointing downwards, right? So there is a huge reversal flow. Now it will take some time to stabilize. So now I'll keep some maximum iterations, and then I'll created a scene out of it. The scene looks like in this way, vector and particle tracks. So this would be in this way. I'll zoom in. I'll maybe run for more time steps. It's just only for demonstration purpose. It may vary with respect to the accurate cell conditions and temperatures and inlet velocities and the particle size. It will change. So it's running. So maybe I'll come after 5 to 10 minutes and I'll show you what are all the outputs and how it is getting varied. It ran up to some time. Now I'll just show you the potassium bicarbonate initially at first time step. After 5 iterations of the steady state, you have seen this is the fraction. Now we will see the increase in the potassium bicarbonate. So it is increased by 200 times. It is visible here. So now what I do, I'll maybe run some more iterations and I'll try to extract the video out of it. And also you can have the reports for different things. Maybe if you want to have volume integrals with discrete phase variables, DPM concentration, potassium bicarbonate concentration, anything over this, you can always find. This is the potassium bicarbonate concentration and this is the potassium bicarbonate concentration. So this concentration increases as the time progresses and this potassium carbonate concentration decreases. So if the potassium carbonate concentration decreases, means more amount of CO2 is getting absorbed onto the particles. These granules, particles or granules, anything it may be. Okay, so I'll run some more iterations and I'll create an animation and I'll attach to this before this video, so that you will have a glance how the potassium carbonate is reducing and the potassium bicarbonate is increasing by taking the CO2 and H2O into it. Okay, thank you.